Group and the Bloor Group. This is yours truly, Eric Kavanagh. I'll be your host for today's event, which is on a really, really hot topic, folks. This is the cutting edge of information management, how to build reliable, modern data pipelines using AI and DataOps. Of course, that refers to artificial intelligence. We're going to hear from my good buddy Wayne Eckerson, president of the Eckerson Group. Then we'll hear from Eric Chu of Unravel Data. Here's a slide about Wayne, 25-plus years in the industry. He and I actually launched the TDWY webinar campaign way back in 2005. That seems like about 1,000 years ago or so, but we've been rocking and rolling ever since. And, of course, Wayne does all kinds of great work with industry analysts and with vendors trying to map out what's going on in the world today. And we are witnessing a major metamorphosis right now. The technologies that are driving the next generation of information management are head and shoulders above their predecessors. This is not an evolutionary change. We're really talking about a revolutionary change in how data is leveraged for business value. And the reason that you needed a whole new class of technologies is because the volume and the variety and the velocity and the unwieldiness of the data is so great and so significant that the old tools simply don't work. So we're going to hear from Unravel Data how they're able to really see deep into these big data architectures and troubleshoot and basically get the stuff running and humming the way it should. And anyone who is in the business knows that if these systems are not running and doing what they're supposed to be doing, money is flying out the window. So, folks, we do archive all these webinars. We're recording this. You can come back anytime and check out the archive. Should be up by tomorrow. Please don't be shy. Send questions using the Q&A component of your webcast console, or you can chat yours truly. And if you're on Twitter, feel free to track me at Eric_Kavanagh. I'll be live tweeting throughout the show. And with that, let me hand it off to Wayne Eckerson. Take it away in Modern Data Pipeline.
Great. Thank you, Eric, and hello to everyone out there. A very hot topic. We're going to double down on the DataOps topic this year because we think it's key to success in the new modern digital era. And in fact, what we're seeing is that companies are building what we call modern data-driven applications that use data and analytics to connect people, materials, products, processes, and machines within a real-time data fabric to create a digital ecosystem. Sometimes I call it a digital organism because these things can sense and respond events and changes and automatically adapt. And when we have that capability and that power, we can support all kinds of sophisticated applications, such as the smart factory of the future that uses predictive maintenance and integrated supply chains to increase efficiency and automation by leaps and bounds. The sharing economy that creates a real-time marketplace of people looking to get rides and drivers were looking to pick them up. Customer 360 applications that pull customer transactions, interactions, and observations from multiple sources across any channel in real time to deliver a complete integrated holistic view of the customer to anyone who needs it, and so on and so forth. So this is the new world that we're living in, and it's really predicated on data and analytics. And by analytics, we're talking mostly these days about artificial intelligence and machine learning. But where are we today? In reality, most data architectures at most companies are still completely reliant on a data warehouse that, as you all know, if you've been in this space, looks like this. It was designed to create a single version of truth. And it does fairly well for what it was designed to do, but there's some liabilities. It's slow to deploy, hard to change, expensive to maintain, not great for ad hoc beyond what it was modeled to support in a dimensional schema, not great for all types of data or big data, large volumes of data, fast-moving data, unstructured and multi-structured data. But it is good for answering known questions. So if you know what users need in a report or a dashboard, you can model that, collect data to support that, and that's really what it's good for. But you know, a lot of people, especially 10 years ago, were ready to throw the data warehouse out in favor of Hadoop and data lakes. But great to see that the data warehouse is sexy again. This year it's kind of seen a second birth. And I think people are realizing that the problem with the data warehouse, other than the things I mentioned, is that we asked it to do too much. It really is one pipeline out of many that you need in your organization to support the multiplicity of applications that your business users need. So a more modern data architecture pulls data from any number of sources, both inside and outside the organization, and pushes that data to multiple targets, both inside and outside the organization, both on-premises and in the cloud. And the ecosystem itself is no longer just one repository data warehouse. It's actually multiple repositories, multiple data warehouses, data lakes, even files, social graphs, regional environments, data science clusters, all kinds of environments. So as you can see, these days, connecting sources to targets and moving data and transforming data is a fairly complex endeavor. So instead of one pipeline that we've traditionally built to support all things data and analytics, we now have multiple pipelines. Of course, the downside here is that this gets very complex very fast. So let's just look at what one data pipeline is about. This is from an article that my colleague Dave Wells wrote called Complexities of Modern Data Pipelines, which you can find on our website. And you can see that on the left side are the sources, on the right side are the targets or destinations. And in between, we have at the top a data flow that moves data through various steps and storage layers to get to its destination. On the storage side, there may be many different types of storage, and within one data flow, there could be multiple storage environments instead of the one just pictured here. To the right of storage, we have processing. So each of those steps in the blue is a place where data is refined and then moved to the next step. And you can see the different types of processing and transformation that occurs in those steps. There's also an overarching workflow that coordinates the execution of those steps and orchestrates the distribution of data across the data flows. And then finally, and perhaps most importantly, we have the monitoring of all this, the performance monitoring, the diagnostics, and the debugging that's really important to keep the flow of data moving efficiently, effectively, and accurately. Now, the issue here is that this is a lot to do, and this is just one pipeline. But in many organizations, there are multiple pipelines. And they're actually, they vary greatly in their complexity. So, for instance, a simple pipeline might be export this data into a CSV file and place it into a file folder. A more complex pipeline might be a move tables from 10 sources into a target database, merge common fields, array into a dimensional schema, aggregate by year, flag null values, convert into an extract for a BI tool, and generate personalized dashboards. And I don't even know if that's the most complex out there for sure. But there's a variety of different types of pipelines. And then you combine all these together, and you've got something that's fairly complex to manage and monitor. And I would call the collection of data pipelines a data supply chain. So keeping track of all these and orchestrating the movement of data across all these steps is very complex. There's also different types of pipelines. The ones we've been talking about are execution pipelines, where we've already set up the pipeline. Now we just need to move the data through the various steps. But there's also a development pipeline, which moves data from requirements to development to testing and into production so it can be executed. So that's more of the innovation side of the business, whereas the execution pipeline is more of the operational side of the business. So what we've decided that to manage this complexity, we need something that people are calling DataOps, and that's a play off the term DevOps, which has been very successful in the software engineering space, bringing rigor, accuracy, and speed to the development of software applications. So very recently, people have tried to borrow those concepts and move them into the world of data. So as you can see here, DataOps applies rigor to the development and execution of data pipelines. And there's four main components, really, of DataOps or dimensions. The first is Agile, and that's where we're using Agile methods and techniques like Scrum and Kanban, where we have self-organizing teams engaged in short sprints to develop fully working software that can be tested and reviewed by business users and requirements reshuffled after every sprint. That's pretty well known. That's pretty common in the data analytics space already. What's less common is the application of DevOps techniques. And this is where we use things like continuous integration, continuous deployment, and continuous testing to really accelerate the deployment lifecycle of these data pipelines and improve their accuracy at the same time. So go faster and do it better than we had in the past, where we relied a lot on manual steps in the process and human involvement to make things happen. A key part of DevOps are these repositories, code repositories, configuration repositories, so that we can be sure that we can check code in, especially in a large development environment. People aren't overwriting each other's code, and we can set up an environment through a configuration repository, more recently through containers, to ensure that the environment doesn't change so that what we put out there into production is not going to break. On the total quality management side, this is all about testing and performance management, performance metrics, continuous monitoring and improvement. And it's also about just monitoring and testing everything that we do so that we can detect errors as soon as they happen and begin to put in place processes to prevent those errors from happening in the first place, as well as to continuously automate every step along the way. And the final dimension of DataOps is borrowed from the lean manufacturing environment, where we do try to automate as much as we can by orchestrating, using orchestration software to trigger the use of different software tools and products to ensure the efficient flow of data through the pipelines. The benefits of DataOps I've hinted at. Speed on one hand, faster cycle times. We can make changes more quickly. People don't have to wait as long. Quality, fewer data defects, even though we're automating more and more. Collaboration, so instead of creating your own data pipeline in your own little world, now we work together because we have the means to do so and the tools to do so. So more coordination means that we can move faster and we can reuse things instead of creating them from anew and from scratch all the time. And finally, a greater business satisfaction. They have more trust in the data because it's more accurate, more trust in the process because it's faster and meets their needs in a more timely way. So at Eckerson Group, we've developed a framework for DataOps to kind of explain what this is, because it's kind of a sprawling area. And I must admit, when I started looking into this last year, I was like, what is this? It's kind of amorphous. It was kind of hard to pin down, like nailing a jellyfish to a wall. At least that's how it felt to me. And I wrote a report on this, which you can download from our website. And this is, well, actually, this is from one of a blog that I wrote recently. So here you have a typical data pipeline. You have the source systems, and you have the consumers on the right side. In between, you have data ingestion, data engineering, where we do the transformation, and data analytics, where we're consuming the data. On top of this, we have data processes, which I've touched on already. We have continuous integration to develop new capabilities, continuous deployment and testing to deploy those, orchestration software that helps coordinate the data flow and the movement of data from step to step in an automated way, and continuous testing and monitoring to make sure everything's going as designed and that we can detect bugs very quickly and remediate them. On the bottom here are the technologies that we use to support these data pipelines. So the top of the circle are the processes, which are supported by, as we mentioned, agile techniques, code repositories, configuration repositories, and containerization. And the bottom are the technologies that we typically use and that we coordinate with orchestration software. So data capture software, which ranges from everything from SQL and file transfer to change data capture and replication, and now streaming. Data integration, where we're integrating data via ETL or ELT, master data management, data unification, data quality and cleansing, validation, and all that good stuff. Data preparation, which is more data transformation done by the business using data catalogs, data lineage, data governance, data collaboration software. And then finally, the consumption of that data for decision-making and analysis. So this is our framework for DataOps. I think it gives you a pretty concise view of what it is. Typically, people point to the process at the top of the circle as DataOps and DataOps-like tools. And in a large way, they're coordinating the technologies underneath to drive the pipeline in the middle. AI is a key part of DataOps, like it is in most things these days. So where you see the star.
All right. Did we lose him? Are you there, Wayne? I can't hear you. Well, you can see he's giving a summary here: goal of architecture, goal of DataOps, automate, monitor, and optimize data pipelines. We've heard quite a bit of interesting insights so far from Wayne about really how this whole industry can be pieced together. And now I believe I can hand it off to Eric Chu from Unravel Data. So, Eric, I'm going to make you the presenter.
Okay.
And take it away. Go ahead and share your screen, I believe.
Yes, can you see it?
I can see your screen.
Great. Thank you, Eric and Wayne.
Yep.
Hello, everyone. This is Eric Chu. I'm the VP of Data Insights and part of the founding team of Unravel Data. My background is in database research. I got my PhD in computer science, focusing on database optimization from the University of Wisconsin-Madison. And after that, I worked at Microsoft SQL Azure, working on their the first database management service for SQL Azure, circa 2009 to 2012. After that, I joined an ad tech company called Rocket Fuel, where I was responsible for the whole big data stack that has multiple clusters and thousands of nodes. And that's where I faced many of the big data challenges that later on, when I joined Unravel and talked to different customers, I realized that these big data challenges are not unique to my last company, but in fact, every company that deals with big data faces these challenges as well. And if you're a data engineer or a data scientist or an ops, I'm sure you have experienced that many of these problems actually they repeat. There are many patterns, many common problems. And the upside of this is that we can actually learn from these and tackle this problem effectively with AI. And that's what I'm trying to tell you today. So as Wayne has pointed out, today data no longer resides in a single database or a data warehouse, but it's basically a data ecosystem that we have to deal with. You have a variety of sources of data coming in, being processed and ingested with either in real time or batch processing, with a variety of technologies like Hive or MapReduce, even though that is old, is still being used by a lot of large companies. And then you may use Hive on Tez and or Impala or Spark to do modeling, and all this are using Kafka to send them in different messages. And all of these data in the process form could be stored in different places and serve different purposes, like more modeling pipeline, some BI applications, etc. And you probably will agree with me that managing this set of distributed apps is extremely difficult and expensive because there oftentimes you would see a failed app, or you would see things don't go as fast as you expect them to, and there are many factors that can cause that result. It could, if we're talking about an individual SQL app, it could be that it is slow because it has a bad join, or you may not have the right level of parallelism because you don't have the optimal container sizes or the number of containers. Or it could be data layout problem, like too many small files, or even hardware problem. Like your app may be completely fine, but one of the nodes on the cluster is actually failing. So, and the work is kept being sent to that node. So all of these things, it's just overwhelm users to really understand and make it very difficult to understand what is the root cause for the performance issues. Now, so how do people actually currently solve this problem? Imagine we have a Spark application, and what they do is they have to look at different UIs, like the Spark UI, the Resource Manager UI, to look at the app, find relevant metrics, and review the stages, look at the executors, and deep dive into different sources of data that would hopefully shed some light on it. And because the distributed nature of the application, there are many places you have to go look, and you have to have a lot of expertise knowledge to understand what's going on, to piece them together, and you rinse and repeat. So what we've been working on is to ask this question: can we make this easier? Imagine this is only one system, one user, and one app. Now, imagine if in a real company you have a lot more users, a lot more apps, and a lot more systems. So what we're trying to do is create a world where instead of going through all those manually, different sources of data and requiring people to have a lot of specialty domain knowledge, can a user, like an app developer or data scientist or and so on, just say that I have an app and I have a goal, and the goal can be different. It can be different goals. It could be speed up. It could be just make sure it runs because it's been failing, or to meet some SLAs, and just declare that goal, and then have a system that can find out based on a run to tell them, hey, I find some recommendations that you can use to tune this application to make it faster, and then maybe the system will keep going when you go off to check your email, and then meanwhile the system would find another run, would find other configurations that make it even faster, and maybe even if it runs longer, analyzes more, it learns and finds out, oh, actually there's yet another configuration that you can use to make this run 90% faster. And so what I want to tell you in this session is basically that if you approach the problem with the right tools and the right information, actually we can do something like this. So before I go on to show you what we do, let's look at the video. So this is Unravel, where you can see we have a lot of apps, and then this is one of the apps. And on the right side, you can see that this is a Scala Spark program. And then on the left side, you can see jobs associated with it. and then you see that this job duration is 6 minutes, 15 seconds, and so it shows you all the main the metrics of the application. And then Unravel also provides recommendations for tuning an application. And then here you see a lot of these configurations that actually, you can set it with different values to make it faster. But as a developer, you probably don't really care about like what these ops are, configurations are, and what is the right value, what is the optimal value, and you just want to create a session to actually to auto tune this. And so over here, you can specify that create a session to automatically tune this application. And notice that here we actually allow users to specify the tuning goal. And here we pick efficiency, but there are like multiple goals you can tune, like reliability, etc. And then other part is specify your program, your arguments, and the maximum number of times of runs that I tolerate, that I could, because every time you run something, especially on the cloud, it may cost something, and it may take some time, take some resources. So to find out how, so people want to specify a cap of the resources they're willing to spend on finding out the optimal recommendations, configurations for this app. And as you can see here, then that a session has been created, and on the right side, you can see the progress of the analysis that is going on. So after a while, you see that, oh, we actually have found something that will make make this app, the new run, run much faster, going from 6 minutes to 1 minute. But it will keep going, and then see that, or maybe it has another run to try different configurations to see if it could get even better results. It turns out that this time it doesn't necessarily give you better, but then the analysis stops there. Now on the right, you can see that the duration of each run going from 6 minutes to 1 minute, and what we are trying to get at the end is running these the same app multiple times, probing what would be a good set of configuration and try, and then show to users, hey, this is what you should set to make it run fast. So with that, I'll keep going to the next slide, and let's take a step back to and look at this Unravel session that I just showed you. So when we talk about a session, what we are really trying to do is to let users just provide an app and declare a goal. The goal can be efficiency, could be reliability, could be speed up, and SLA, and the app could also be of various types. It could be a SQL app, it could be like a Spark program, Scala program that we just showed, a DAG and workload. So there are two dimensions that we are that is the crux of this session, and this is actually something that really we can use AI to effectively address this problem. I know you probably have heard many places, many people say, oh, we use AI, we do it, or machine learning, but this is indeed a problem where without some automated decision making or automated learning, it is impossible to do a good job of. So what do we mean by, so what is this Unravel sessions architecture? So the crux of this sessions architecture is really the probe algorithm, where we try to look at what the data we have, and the goal is to try to find out a next set of configurations that will maximize the benefit according to the goal. And we have some, and then another component of this architecture is the orchestrator that actually takes in this the results of the probe algorithm and run it either on your on-premise cluster or on the cloud, and so it will result in another run. And as we get another new run, then we have more. It turns out we will have more historic data, and then which will feed back into our recommendation algorithm. And one very important part of this loop is actually the user. which can actually change the goal. Right? So, for example, you can imagine someone who wants to speed up their application, and of course, they will say, "Oh, I just want it to be as fast as possible." Like on the cloud, for example, that could mean you need to spend a lot of resources to make it run fast, and that could be very expensive. So maybe at first they would say, "Oh, I would want this application to run in 2 minutes," but it actually would take, let's say, $1,000 to run it in 2 minutes. But then they would say, "Oh, actually, it's not that important to run it in 2 minutes. I could run it in 5 minutes, and the cost would be $500, for example." So you can. So the goal actually is not always that you want it as fast as possible, but it's a combination of the business requirements and the cost limitations. So how do we do that, right? If we take the Spark application we just saw, we see that there are a lot of multiple configurations that we look at, and we can provide recommendations. And in general, what we do is we treat this set of relevant configurations as a vector, and we model it kind of like like a surface response. So on the right, you see this picture or this graph where the y-axis is kind of the response time, and the blue, so the lower is better, and you can see the blue area. And basically, the plane horizontally is the two dimensions of the variables that we consider. And so there's this, you can map this response surface, and what we want to get eventually is that getting a set of x, getting a vector x such that the response time is the lowest, or in this case, in the blue area. So this is basically what I just said. The goal is finding the setting of x that best needs to go, and the response surface is unknown. And that is the challenge of this problem. But this methodology is actually not something new, but it's a very common concept in AI. And the way we do this is basically we have some kind of bootstrap algorithm that, given a run, we look at or maybe even multiple runs, right? Look at the history and get this relevant information, and then we would the probe algorithm would actually decide the next setting to try, and then we have the orchestrator that we saw in that architecture that would take this probe algorithm result and run it, and then we repeat this process. Because every time a new run comes in, we have new data, and then the probe algorithm will actually consider both the new run, the latest run, and the history, and come up with and make the decision of whether to keep trying something new, or we have arrived at something that is the best. And that is governed by some kind of stopping condition. In the example in the video, it went very fast, but one of the parameters before we start, when we specify the session, is how many runs you run, and I set it to 3. And what that means is basically I said I'm willing to spend resources to run this app 3 times, and then from then on I'll use the best configuration that we see we derive from that experiment as the result. So that's one example of the stopping condition. So now, if you look back at this this picture, this result surface, and then consider like one of the parameter that we try to optimize, so it's in 2-dimensional, and then if you look at the left side, imagine the actual ideal response is actually in the red, which is unknown, but we have run like 5 we have done 5 probes as indicated by the circles, that actually give us a model, a regression model that is shown in green, with the error here with these bars. And I know I skipped some slides in this demo, but actually what we are what we are using is a Gaussian process to do the error estimation, because every time when we do some kind of regression model, the residual, there's just some part that is unpredictable, and we use the Gaussian process to estimate that error. And as you can see, right, actually there are these are the blue line is the response time, and you can see two peaks, but they actually come they are the result of different part of the algorithm, right? So in AI, there's this exploration versus exploitation tension, and you can see between these 2 points, this is actually what we see is we have seen the best results, and we wanted to exploit and keep probing for the next value we want to try because we have seen the best result, and that's an example of exploitation. On the other hand, for exploration, here we actually wanted to try this out for the next value that we wanted to probe, because we haven't had any probes in this range, and so the unknown is there's a lot of unknown. So exploration again basically means it's not very certain. We wanted to explore that area, and that's why we wanted to probe it. And then exploitation is basically the idea that based on some observation, we know that is the right direction, so we want to keep going and try to see if we can get an even better value. So this is basically a balance between high data. When we don't have a lot of data, we have high uncertainty, and on the other end of the spectrum, we have a lot of data, and so we have relatively low uncertainty. But both of them basically serve to drive serve to determine what we want to try next. And this is by no means easy, right? So because this has a diverse base of data and a lot of uncertainty. When we talk about a goal is very specific. It has and it depending on what goal we're talking about, the approach and the probe algorithm could be very different. Right? Whereas, for example, making the app faster would call for a different algorithm from making an app more reliable, because you can take because when you want an app to be reliable, that means you cannot afford to be as risky and be as closer to the resource, cutting too close to the resource limit. And then the app also, there are various types of apps. There's SQL, there's program, and then when we talk about, so even though we have settled in our last example, let's say we consider a Spark program and we want to make it faster, then how we approach this problem is still limited to whether we have trained models. Yes, no, partially, that will all make affect the ultimate certainty and the accuracy of the recommendation. And is similar historic data available? And if there is, then we can leverage that. And also, at the end, it's like how soon user needs the answer. Sometimes people just can't wait, right? So maybe they just want to start with even the first one with some recommendation. Remember earlier, there's a picture where it says the first one will give you 30% performance improvement, and maybe that's what they need. They just want something faster, or maybe it's a very important, significant pipeline that improving the performance means a lot in saving the cost, and that's when you want to invest the cost and spend more time on running running a session and try more runs to find a better as best configuration as possible. So all these basically illustrate how diverse a space that we're dealing with in the probe algorithm. How am I doing in time? Okay, so I still have a few minutes. So I just want to highlight some of the lessons we learned from building this session's architecture. So what the probe algorithm is very specific to using it's very specific to the problem we want to solve or the goal we want to solve. So what the lesson we learned that is we don't want to do a very general algorithm, but look at the specific problems that we want to, the aspect of the improvement that we want to solve, like if it's like a, let's say, executor or a container, that kind of like sizing, number. So all of those, we would have a specific algorithm, and then we would combine them and look at what matters more among these different models. The second lesson we learned in the work that we've been doing is any time when there is some cheap probe that we could leverage, we should do that because it gives very fast estimate that would help drive us in the right direction in searching for the optimal configuration. And the third part is so how do we get this data? So to analyze, to come up with recommendations, you need data. And this is where it is extremely important to have a full stack to collect all the relevant data about the application. So by full stack, it include the application data, like the SQL query, like the query plan, all the logs, and all the metrics that we can get our hands on. And the more we get, the richer the model is. And then leverage it like overall over time. When you run more, then you have a richer history which can feed into the learning algorithm. And the last lesson is that we have to keep user in the loop, right? Because users, like I said earlier, the goal can be different depending on the circumstances. It may not always be like one-dimensional, like driving the time to be the minimum. On a cloud, you have to consider also the cost, and maybe even on premise, each application may have a limit on may have a cap on how much resource you can use per app. So you have to take into these limitations, and maybe after that, then the users will change their goal. So what I've just talked about is just auto-tuning about one single application, right? And trying to demonstrate that AI indeed is a very appropriate technology to address this problem of optimizing big data application performance. But beyond application tuning, there are other kinds of use cases that we also do that also leverage similar techniques. So actually, root-causing failures of distributed application is kind of covered by what I just talked about. It's like go hand in hand with making it fast. But before you make something fast, you have to make sure that application runs first. But going beyond the single application, you have also the SLA management for streaming data pipelines, or even a workflow of multiple applications. Right? And those are perhaps more important from a business standpoint. And then at the end, you also have the holistic cluster optimization. So what we mean by that is instead of looking at each application's configurations, are there some configurations that are so shared in common by all these applications that it is best to look at them horizontally and find out what is the best average value of those configurations and set them as the default. So any applications that come into the cluster would automatically pick up those default recommendations, the new better default value. It may not be the most optimal to that single run, but it's the best average out of the observed workload. And so all these problems, we're tackling this with a similar AI philosophy of leveraging the data that we track, Unravel, monitor all the full stack of the data, and then learn from it and find out the best values. So I think so that's the last slide. And so what I want to quickly go over is basically that very soon we'll have a booth we'll be in the AWS Summit in Berlin, and we'll have a booth. And if you happen to be in Berlin, going to that AWS Summit, feel free to stop by our booth. And then if you happen to be from the Bay Area, you're going to the Spark Summit in March in San Francisco, we actually have 2 talks there. So that's my last slide, and I will get it back to Eric, and we can move on to the questions. Mm-hmm.
Sure. No, those were some excellent presentations, and I like the way you kind of showed the topography of the scenario there. Go ahead and share your screen again so folks can see that.
Oh,
Go ahead and share your screen. Yeah, I'd like to kind of dive into that. So is it fair to say that once Unravel data is deployed in a particular environment, slowly and incrementally and even quickly sometimes, it's learning more and more and more about that landscape, identifying similar patterns when they arise? And I'm guessing a lot of that is fairly dynamic, right? In other words, when it finds the signature of a problem, that is codified. It remembers that problem, and if those characteristics come together again, it knows what to do, right?
That's right. So once you install Unravel, it actually would start tracking all the applications that run on the clusters, and we collect all the data in the full stack, so we have the visibility, and that is what enables us to be able to determine what is the right root cause. Because if you look at this slide, there are many of the contributing factors from different levels, and without tracking full stack of the telemetry and the metrics, you may be missing something, right? So and then over time, when we keep this history in the internal Unravel model, which by the way is on the customer's premise on the cloud. Like it's not a service, so no data is leaving the customer. But all this data about how the applications run will be stored within Unravel, and Unravel can have algorithms to learn about this and make better recommendations.
And can you fine-tune the system? In other words, can you tell it what you really want to achieve? I want to get a service level agreement of 10 milliseconds, for example. Is that something that Unravel is capable of enabling?
So right now, what for the workflow part, so that's definitely a goal that we're trying to make. What we are doing currently is to show people what the difference is between different instances of the workflow, and then show them what is different between them. That makes one instance much slower than the other one, right? Because it's a very common problem where a team may have regular workflow that runs every day, and then suddenly on a Wednesday it spikes up, and we don't know what happened, right? So bringing visibility and drawing to the root cause is the first step, and then depending on the root cause, then we can talk about, can we guarantee it, right? Because sometimes because basically different root cause calls for different solution. If the root cause, for example, is something about, let's say you're going to that workflow example, right? Maybe your instance that suddenly spikes up in time is due to a lot of data coming in for that. Then you have to look at why that you suddenly have that much more data compared to other instances. But maybe you have the same amount of data coming in for that workflow, but then some other rogue application is taking all the resources on the cluster. And that's why your workflow doesn't have enough resources to run, right? So those are two examples where that will actually result in very different mitigations. So,
go ahead.
Yeah. So what I was trying to get back to about like guaranteeing like what the different goal is yes, that's at a high level, that's what we're aiming to do. And when I just showed you about the automated the auto tuning, it pertains to one application, and at an application level, individual application level, it's easier to do so. On a workflow level, it has more external factors. So it's actually not that simple, unfortunately. So and that's why this answer is so long. But I hope you can see at least the complexity in dealing with it. And it's very important to simplify it as much as possible for users.
Sure. And when there's a change in the topography, when, let's say, there's a new version of Spark that's deployed, or there's a new big data application, Unravel just accesses that information and moves on, right? That's just one more facet to kind of build the picture of what's going on, right?
Yes. So the bottom line is that we need to be able to observe that such changes have happened, right? Because that could be one of the contributing factors. So what we can show you is like in the video, again, it's very fast, I apologize, but basically in that session where there's like a comparison grid where you can select two instances and then they will compare the different metrics, the main metrics. So what you just said, the different version of Spark, it could be because of that something, it broke something, right? So we need to be able to highlight that. And again, the mitigation always depends on what the root cause is. Sometimes it's easy to configure, like if it's a configuration, then we could always try something automatically. But if it's a data layout problem, then in our auto-tuning session, we'll just have to say, hey, we detect that the root cause is actually due to like too many small files. And that's something like beyond Unravel's capability to like stitch files, right? So that's something that it will stop and it will tell users that, hey, you first need to address that small files problem first before trying this application again. Skew is another example, right? So so it really depends on what problems we're talking about, but the first step is detecting that problem and then taking a very opportunistic approach. Like if it's something that Unravel can do, it will do for you.
Wow, that is really fantastic. And, I've often thought to myself, systems management has always been challenging. It's always been difficult, and we're getting better and better technology to manage that and to really understand. But I've often thought to myself, there is a certain analogy to calculus. And for those of you who took calculus class way back when, you might remember that solving a calculus problem really requires a sort of reverse engineering that's to be done, meaning you have to kind of figure out the pattern of the challenge and then dive in. And it seems to me that with your ensemble approach here, you really cracked that nut, because by taking that ensemble approach, you can run a bunch of different algorithms on the same data set and very quickly ascertain which one is going to get you to the solution most expeditiously, right?
Yes, that is the approach we're taking.
Yeah, that's really impressive. Have you seen patterns where there are specific kinds of failure that are more common than others? I mean, network failure, for example, code failures. Is there any general pattern overall that you've seen of what really causes the trouble?
Yeah, and the patterns really vary by the app type, right? And so if you look at today, what technologies companies with big data use, Spark, for example, is very, very, very common. That's why I use that as an example. And one of the most common failures is basically out of memory. And when that happens, it's very difficult for users to know like where that memory, how much memory I should use, and it becomes because especially when it's like a Spark program. So that I would say is one example that jumps out. Node failures, I think those happen, but they are relatively rare.
Okay, and we've got a couple really good questions from the audience. Here's a very specific one. Does the algorithm dynamically adjust in varied platforms? In other words, from a 4-core VMware to an 8-core, is it going to automatically, dynamically adjust to leverage those new resources?
Yes, because it depends on if we have visibility to whether that platform has 4 vCores or 8 vCores, right? So that's something basically Unravel can see, right? And it's in consideration in the algorithm when it computes about the parallelism aspect. Okay.
This is just amazing stuff, and you guys have been working on this for a while. When did you first begin working on the kernel of the technology?
So so this all goes back to well, before that I should say one of the co-founders is a computer science professor at Duke University. So he also is a database professor, and this originally started as a research project when he was back at Duke, and then he and another person, the CEO, founded this company to at first actually to see. Not so much to think about like making it big, but just more from an academic point of view to see if this approach works, right? So back then it was basically just looking at a run of a MapReduce job and looking at the configurations and try to see if there are better values for that specific set of configurations to make it better. So that was back in, 2009, 2010. And then I actually knew the professor back when we were in grad school, and I ran into him in one of the Hadoop summits like in 2012, and then we basically were working on similar problems, but I was at my last company. So we collaborated, and then I joined in 2015. So it's a long journey, and then and then during this journey, you see the technologies keep evolving. Like back in 2012, a lot of it's mostly Pig and MapReduce or Hive on MapReduce, and then Spark was just starting, but it's gaining traction quickly. And then looking at now, you have a gazillion different technologies, right? So even now we don't support all the technologies out there. There's too many. But we support the most common ones, driven by business requirements, like what our customers use, and then also have to go deep besides breadth. So it is challenging to say the least.
Well, and what's interesting too is the applicability of this technology goes far beyond performance, far beyond keeping the trains running on time. It seems to me there are some very powerful value propositions around, for example, risk management, data governance, security. All of these domains can benefit from this technology, right?
Indeed. So we are a startup after all, so we have to take it one step at a time and make sure that we address the performance problem very well. And again, even when we just talk about performance, it's not about making something as fast as possible. It's like given the set of limitations and requirements, right? But and we wanted to make it easy for users at the end of the day.
Mm-hmm. Well, and that root cause analysis can be so challenging because of the complexity of these environments, because of the amount of pressure that's on these systems. So the fact that you can use this technology to deduce what really did happen, get to the bottom of things, that's going to solve lots of problems. And again, the system learns over time, so you can kind of knock off those problems, and you're pretty reasonably sure you're not going to have those again, so you can dig deeper and deeper into the infrastructure, right?
That's right, and then also just the distributed nature of the system. To really understand where the failure comes from, you have to look at many places, and to do that manually, it's a pain that many of us have experienced.
Mm-hmm. Yep. Okay, we got a couple more questions here. I'll try to throw out before the time is up. Well, here's one question you kind of answered already. Who is the intended user of the software? And it could be an analyst. Again, it could be an IT infrastructure team. It could be a risk management office. It really could be anyone who wants to know what's happening out there in that world, right?
Yes. So in the end, actually, all the companies with big data have these similar roles, right? So you have the application developers who write the application. They would benefit from drilling down into each application, looking at the errors, trying to figure out if you can get it to run or make it fast. You have the DevOps who are interested in the overall throughput of the clusters, and then and make sure just like things don't fail or like there's no rogue application that takes down the cluster, etc. So they could monitor this, like all the apps that Unravel tracks from Unravel. And then you have the architects or the team leads or people who are responsible for the cost, right? Especially on the cloud. I haven't touched on this in the demo, but a lot of our customers actually they started using on-prem, and then they're moving to the cloud, migrating to the cloud. And then one key problem is to figure out like how much clusters, what's the cost that they expect to pay. And so it's a very, actually quite complicated question to tackle, right? So you have to assume that the performance will not get worse when you move to the cloud. And to guarantee that, how many nodes, what are the node types should you get to meet the goal? So again, that is an excellent question to leverage AI and learning to tackle. But the prerequisite is that you need to first have the history, which Unravel has done for this customer because it has been running on their on-prem clusters.
That's great. Yeah, and then I guess one last question, because you kind of hinted at this. I joke on our radio shows that we went from talking hybrid cloud, which of course is cloud and on-prem, to multi-cloud in about 2 weeks, because multi-cloud is the future. You're going to have Azure, you're going to have SAP, you're going to have Oracle, Rackspace, Heroku. Google Cloud Platform is getting very serious. This kind of technology should be able to see into all those environments to at least a degree, right?
Oh, and definitely, and that is actually what we designed for. When we started this product, it's right from the beginning. It is designed to be running on different platforms. So on-prem, you can run it on Cloudera, HDP, MapR. On the cloud, we can do AWS, Azure, later on GCP. But it's designed to support different platforms. The idea is clear, right? No matter where you run these big data applications, you will see similar problems. So it's very important to have a single pane of glass. That's what we are aiming to become, that collects all this information from different sources and then show them to users in a single place and then tell them what to do, right? And not just show them, but also analyzing the data coming from it and telling people what is the right thing to do.
That's fantastic. Well, folks, like I said, we archive all these webinars for later viewing. The archive should be up by tomorrow. And with that, we're going to bid you farewell. We'll also try to get a copy of the slides for you folks. This has been an absolutely fantastic presentation. Thank you to Wayne Eckerson of Eckerson Group. Thanks to the folks at Unravel. We'll talk to you soon, folks. Take care. Bye-bye. All right, and speakers, stick